All right, thank you. Thank you, everyone. So, yeah, let's get into it. So, you already introduced me. So, a couple of things have changed since then. So, I became the head of R&D at Entropica Labs. That did not happen in between me sending the bio to the QHack people and the presentation. But that's what's one of the new things in my life. Entropica Labs is a company, is a startup in Singapore, trying to make quantum computers useful, like many other startups out there. You may have interacted with me already because I'm a developer and maintainer of OpenQOA. It's an open source package sponsored by Entropica to solve the quantum approximate optimization algorithm. And indeed, if you participated in QHack in the last couple of years, you might have heard a few talks from us on that topic. But today, I'm here to talk about something slightly different. So today I will be talking about the role of software. It's a very packed day, so on purpose I try to make this presentation lighthearted and simple. And I'm wondering, maybe even a bit too simple. That's how I see software. You have the user on one hand, and you have the quantum computers on the other one. And software is the thing that bridges that gap. It's what takes you there. I know this is trivial, but my point is trying to argue that it's perhaps not as trivial as it sounds at first. So today, I argue, we know the stack fairly well. So we have a well ironed out stack to connect and use quantum computers. My claim is that quantum error correction will change things. It will add an extra layer of complexity to this stack. And I think for everyone interested in quantum computing in general, this is something they should know. Maybe you will not end up using these things directly, totally possible and totally fair, but I think it's worth looking into that. And anyone in the industry out there will probably have to do so in the next years. So let's get started. What's the flow of a quantum algorithm today, at least? So you start wherever really you want to start from. Could be a book, good old Nilsson and Chuang. It could be a paper on the archive. It could be PennyLane. It could be OpenQA, Qiskit, your favorite library. Wherever you start from, you end up having an ideal quantum algorithm. And once you have this ideal quantum algorithm that usually you write out as a circuit, but it could even be in a different formalism. It could be measurement based or anything you want. Then you use software to get an executable quantum program. This is like the flow, really, like how we tend to think about this concept. And of course, eventually you will send this off to a quantum computer. So executable here just means that it's something that if you send to a quantum computer, the quantum computer will know how to run that particular program. So far, I think so good. Nothing too revolutionary here. Ideal quantum algorithms. What are those exactly? So the idea is that each qubit in your ideal quantum algorithm is treated as a perfect qubit. So what I mean by that is that your ideal qubits are in a one-to-one map to the physical qubits of your hardware device. This will change later on through the talk, and if it sounds a little bit not very clear right now, or a bit confusing, I hope it will be clearer as we go through. So it's a very simple example. In this situation, I have a classical quantum circuit over here, my wires and my gates and whatnot. And all I'm saying is that when I think about this algorithm, I hope you can see my mouse, the first wire goes to one physical qubit on the device. In this case, it's the IonQ harmony device. Likewise, number two, and so on and so forth. And of course, I can map them anywhere I want within this hardware. But the important thing is that each qubit in my ideal quantum circuit is, in some sense, perfect, is ideal. It represents everything I would like to have from a qubit. So in some sense, what I'm saying here is that we kind of fundamentally assuming there is no noise or errors. And this is perfectly fine. If I want to design a new algorithm, this is a perfectly valid way to look at a quantum algorithm. But it's nonetheless a strong assumption we are making there. And I will show you as we go through this presentation how quantum error correction will sort of challenge this idea of a one-to-one map. And when I said there is no noise or errors, again, in the spirit of making the presentation a bit lighter, I I tried to ask ChatGPT to come up with a few pictures to illustrate, and indeed, it reminded me of when you try to model something in the early physics courses at university, and you say, well, okay, I have a unicorn, but fundamentally a unicorn will just be a sphere, and there is no air friction and it's vacuum, so I'm just gonna have a sphere rolling down some slope, and that will be my unicorn. No need to actually sort of go into the details of how the unicorn has 4 legs or whatever. So we covered the ideal quantum algorithms. The next step is the executable program part. How do we obtain executable programs with software? Again, I asked ChatGPT to draw a presentation ready image of a quantum circuit based on Qiskit diagrams. That's what he came up with. I thought it was funny enough that I would leave it. So that's my ideal quantum circuit. Any algorithm, could be Grover, could be Shor's algorithm, anything really. And the idea is I have some hardware and I would like to run this algorithm using that particular hardware. In this case, I just picked the IBM Brisbane topology hardware. And the claim is that today we know the steps pretty well. So first of all, you will have to sort of translate your ideal quantum algorithm using only native gates. So not using gates that are not supported by the machine. You'll need to select which qubits you want to use. I have 128 qubits here. Maybe I need all of them. Maybe I need a subset. Which ones I need to map to my ideal quantum, my ideal qubits in the circuit to the hardware. I may need to do some routing, some pulse control, schedules. The list is long. And of course, the list changes if I deal with ion traps or neutral atoms or photonic devices. But at its core, these steps are relatively well known. They may be difficult, but we kind of know them by now. This is all amazing, right? Having worked on NIST devices for the past 4 or 5 years, actively trying to run computation on them, I surely relate to the next meme, and I guess many of you do as well. Just leave it here for a second. Every time you try to run something on a quantum computer is the same. It turns out that you always hope the results will be better than the rubbish at times you get back. And of course, what happens is that there are a lot of noise. There's a lot of errors, there's noise, and things never quite work the way you expect them to work. And that's fine, it's part of the game, but we need to do something about it. So there are 2 strategies we can employ: error correction and error mitigation. Now, first of all, I want to say these are 2 different things. So my goal today is not to claim, oh, error correction is so much better than error mitigation, or the other way around. They're just different things, different ways of thinking about how to deal with problems and how to solve certain problems. So error correction, a technique to correct errors by embedding your ideal quantum program within some quantum error correction code. Now, this will be a bit more clear later on what it means, but fundamentally, the goal of error correction is to correct errors. You want to know what error has occurred on your device, in your computation, and you want to do something to fix that error. On the error mitigation side of things, on the other hand, we have a set of techniques that try to improve the fidelity of the operations you're performing on your quantum device. And this could be the operation themselves or the measurements when there is some noise. Indeed, you can try to apply error mitigation techniques to an error correction code. So the 2 things are not exactly opposed one to the other, but their goals are slightly different, and that makes a big difference in my opinion. At Entropica Labs, we don't really feel we have a choice. We have decided that we want to focus on quantum error correction. And that's what I will talk about after. I also want to point out that there's a lot of really good companies, some of which we'll also talk today, the later presentation, that focus on bits and pieces of error mitigations, and they're doing a great job as well, trying to improve what you can do today with quantum processors. So it's really not a fight between the two things. Now, what's the simplest error correction code? Now, the question is, I want to impress someone. So somebody's coming over for dinner and I want to bake a cake. I want to make sure that that will be a success. What can I do? What are my chances? What are my options out there? Well, one thing that I can do is I'll just bake the same cake 5 times and pick the best one. Now, that's a very simple sort of error correction algorithm, if you want, which is based on repeating the same operation over a period of time. Of course, it will take longer and I will need to spend more money buying the ingredients, but it sort of tries to help me making sure that that at least one K will be good and I'll be satisfied with. Now, quantum mechanically, it turns out we can't do that. The reason why we cannot do that is the no-cloning theorem. The no-cloning theorem fundamentally tells you that if I have an unknown quantum state, I cannot make arbitrary copies of it. I can make a copy of it, but I delete the original one, which means that this kind of strategy is just not going to work. Now, we can do something else. What we can do is we can use entanglement. So I took this circuit, which represents a very simple, intuitive quantum error correction code by Staines. Nice notes on error correction. The link is down there. What's happening here is that I have a state, phi, at the beginning, and I have some noise that will happen over time. And what I do is that I encode this single qubit into a system of 3 qubits. This is the original crucial step that sets me apart from the ideal quantum circuit. Rather than considering just one ideal qubit, one physical qubit, in this particular example, I'm going 1 to 3. What happens then is the noise arrives, and then I have a strategy by adding 2 extra qubits and performing some operations to actually correct for the potential noise that has arrived. And then I decouple the information, so I go back to just one system, and then I'm good to go. So what are we doing here is that we're using entanglement to create some redundancy in my information, and this is really the core of error correction, quantum error correction. So what's the flow of a quantum error corrected algorithm? Well, start from the same as before. I have my input and I get an ideal quantum algorithm. Once I have that, I will embed this into a quantum error correction code. I will perform some checks because I want to make sure that this embedding has worked out correctly. So I need to check for error correction and I need to check for fault tolerance. Fault tolerance, I'm just throwing a bit more stuff at you. It basically, in a nutshell, simplifying things, it's a way to look, it's a way to make sure that you're not just correcting errors, but you also prevent errors from spreading out of proportions. And once you've done this, you obtain an executable and fault-tolerant quantum program. So my claim is that we need a new software stack to get executable and fault-tolerant quantum programs. And this is a big deal, and it's changing a lot of the way that we think about just software and quantum computations. So the fault-tolerant stack. The full list of steps you need to perform if you want to make sure that your computation is fault-tolerant is not just long, it's partially not quite fully worked out. We are still at the beginning. A lot of people have different ideas, different plans, but what I can tell you is that it's long and it's complicated. I've picked here just one simple example just to motivate this presentation, if you want, and part of our work at Entropica. So what we want to check is the validity of the syndrome extraction circuit. Now, at the moment, it's a mouthful, so let me break this down. Same circuit as before, exactly the same thing. This part here is the syndrome extraction circuit. So what have we done? Single qubit that encodes my state that I want to preserve. I encode it into a 3-qubit system. And then what I do here is that I add 2 more qubits. I perform a bunch of C-nots, and then I perform some measurements. Now, what happens when I perform the measurements? I get a bit string. So if I get 0, 0, I know that I shouldn't do anything. If I do 0, 1, it means that I need to do an X correction on my 3rd qubit here. And if I get 1, 0, it will be an X correction here on the 2nd qubit. And if I get 1, 1 in my outcomes, an X correction here. So in all of these cases, what I'm doing is that I know how to correct for something. And syndrome, if you look at the dictionary definition of it, is exactly a group of symptoms which consistently occur together. So I look at the symptoms and then I know what I need to do. Checking the syndrome extraction. What does that mean? Let's look at a real example. Here, that's a surface code. It's a complex beast made of many qubits. Each dot, it's a qubit. White dots are data qubits. Black dots will be the ancilla qubits, these extra qubits I put in order for the algorithm, the quantum error correction algorithm to work. Each one of these stars, the yellow and sort of green-bluish ones, is composed by a quantum circuit. And now my task is, well, now I want to run this on a real device. How am I going to do that? Now, if I try to do this, it becomes very complicated and very quickly. And I also really want to make sure that my conditions, the error correction conditions and the fault tolerant conditions, are satisfied. This is difficult. I can't do this by hand because the problems get very quickly too large. I need software to solve this problem. And solving this type of problems will be fundamental as we go through in our sort of quest of making quantum computers useful. So we are in search of this fault tolerant stack because we need software to ensure our ideal quantum algorithms are executable and fault tolerant. And to conclude, this is not just about compilation. I made the example sort of going from a circuit to some hardware and arguing that, well, it's difficult to put stuff on a superconducting device. It's not just about that. It's really about optimizing fault-tolerant circuits. It's not sometimes just enough to come up with a naive fault-tolerant circuit. Sometimes you need to make that work and work nicely. And that's not going to be a trivial task. A lot of software is going to be needed to make that possible. And what I said also applies to all quantum computing platforms. It applies to ion traps, photonics devices, neutral atoms platforms, and you name it. It's not just a feature of superconducting qubits. I just used that as an example. With this, I think my time is probably almost over. So I thank you for your time and your attention. I'm happy to take some questions, and thank you.
Thank you, Leonardo. Really appreciate that. Really liked your talk there. We have a couple of questions, but for those of you who still have questions for Leonardo, he will be on the Discord. So go to the Discord afterwards if you want to bother Leonardo more. Okay, a couple of questions here. We've got one from Catalina. Right, Entropica has a quantum research engineer position on our job board. So you can go check that out if you want to. Our job board's on qhack.ai. So she's just asking, Leonardo, do you have any tips for people applying to the quantum research engineer position?
Be curious. So in general, one of the features that we look for more sort of junior position is curiosity, apart of course from the ability of knowing quantum computing and everything. I know it sounds trivial, but if you want to work for a startup the size of Entropica, we're about 15 people at the moment, hiring is always complicated. So if you want to apply to such a startup, you really need to come across as motivated. So as a general suggestion, I will say that. The rest, like the details of like your ability to use Python or whatever else, those are all things that can be probably fixed over time. But the motivation and sort of that will of working for a startup compared to a bigger corporation is definitely something that we value a lot. Yeah.
Right. There you go. Okay. So that's all we have time for, Leonardo. Thank you so much. Everybody hop on the Discord if you want to chat with Leonardo some more. But for now, Leonardo will say goodbye. Chat
Thank you very much.
Have a great rest of your day.